So we were talking about stacks. Any questions before we get into that? So midterm is tomorrow. It's all about linked lists. So if you have linked list questions, good time to ask them. Yeah.
What's the length of the midterm going to be?
Oh, 8.5 that way and 11 that way.
So just a page?
No, 5 pages, 5 problems, 20 points each.
So no multiple choice?
No multiple choice. It's all programming. But it's either writing snippets of code, like, write a few lines of C that do this, or write a function that does something in particular, right? If you're not sure what I'm asking for, ask, because if I just want like a few lines of code and you start writing a main program and a function and all this stuff, then you're spending a lot of time. And you got about 10 minutes per question. But they're all equally weighted. Some are easier, some are more challenging. So my suggestion is usually read through the problems and go after the ones that you're pretty sure you can make a good attempt at, because they're all 20 points, right? And then when there's time left and you've done those, go to the ones that seem more challenging. Any other questions? All right, I think it's a good midterm, but you'll let me know. So stacks. So remember our basic setup, right? A stack was this thing we could throw information into, and then we could say, tell me what the last piece of information was that I gave you, and it will tell it back to us. And it does this in a way that it remembers every piece of information in the order that we gave it to it, and then it can replay that information to us in the reverse order. So the mnemonic is last in, first out. And so we introduced some terminology. So the main interactions with a stack, if we say push n, this says push data onto the stack, which means save it. If we say pop, that means remove data from the stack. And you're removing the last push data. So the last thing you push, that's the first thing that you pop. There's a stack overflow, which is when you're trying to push, but the stack is full. And that can happen mainly because you run out of memory, right? You have to store this information somewhere if you're going to push it. On a computer, we store it in the memory of the computer, and we only have so much memory. And when that's gone, you can't push anything more. You got a stack overflow. There's also a stack underflow, and that's trying to pop from an empty stack. And that's more a programming issue. Theoretically, there's no reason you would ask for a piece of data that you don't believe is already there. So usually if you're getting a stack underflow, it's a good chance it's a programming issue on your part. It's not like you ran out of resources or something like you do with a push. Sometimes we talk about the top of the stack, which is the data which will be popped next. In some ways, in a pure stack, we don't talk about top of stack, but on a pick processor, we do. So you'll see TOS and top of stack pointer and all that kind of stuff. There's also a term which we will talk about a lot, but it's not necessarily part of a stack. But a stack pointer is basically related to where the top of the stack is. And that'll make more sense when we look at some code. But, you know, if you think about a piece of paper stack, right? So you ask me to remember that you're doing homework. So I write down do homework, and then you say, okay, I have to go feed the cat. So I'll say feed the cat, and while you're doing that, you find you're out of milk, so you have to go to the store. So I'll say go to store. And while you're going to the store, you realize you don't have any money, so you have to go to the ATM. Okay, so I'm keeping a stack for you, right? This is the top of the stack. This is the thing that's going to be popped next. Once you finish going to the ATM, you'll pop this off. You'll return with going to the store. If you find you have to get gas, you'll push the item which says get gas, right? You'll get gas, and when you're done with that, you'll go back to going to the store. When you're done with the store, you'll come back, you'll feed the cat. When you fed the cat, you'll get back to your homework. Okay, so top of stack moves around. It tells you what the thing is that you're going to pop off next, or where you're going to push next. But that's kind of an artificial notion. For example, with the plates in the Chinese buffet, the top of stack is always at the top of that spring-loaded cylinder of plates, right? The top of stack doesn't move. The data inside the stack moves in some sense. And that will, both of those situations will occur depending on how we implement our stack. All right, so basic terminology. So where do we use this in computer science? Because our PC doesn't really do our homework or feed our cat for us. So what's the main place in CPU architecture, operating system, program where we would use a stack? Yeah, so when you do calls and returns, right? So here's our main program, and we're doing some stuff, and we say call, you know, our square root function. And so our computer jumps down to the code for the square root function, and it starts doing some stuff, and it has to do, you know, some magic in there. So it says call magic, and that comes over somewhere, and here's the code for magic, and it's doing some stuff, and it needs to allocate some memory, so it says call malloc. And that makes a call to wherever the code for malloc is, and it starts executing that, and eventually it says return. When it says return, it's got to know where to go back to. It doesn't want to go back to here or there. It wants to go back to here, the line after the call to malloc. But while it's doing that, it needs to remember that eventually when this code says return, it's got to go back to here right after the call to magic. And then if somewhere else in this code, we've got another call to malloc, right? That's got to go over to malloc. And this time when malloc hits its return, it's got to come back here instead of there. Right? So all that stuff needs to be kept track of, and a stack works perfectly for that. Basically, when you call, you save the return address on the stack. So when you call, push the return address, which is the address of the next instruction. And then when you say return, and then, you know, then go to what you're calling. So a call is like a go-to. You just save the return address first. And when you say return, pop off the return address and go there. All right, so stacks work well for this. Every time you make a call to a function, you save the return address on the stack, and when you say return, you pop the last thing that was pushed on the stack that should have been the next instruction after the last call that you did. You jump back there, that's how you come back from the call, and you just continue. When your main program says return, well, you didn't push anything on the stack, but somebody else did, right? Bash, when it called your program, basically threw something on the stack, and when you return, you're jumping back there. So there's stuff that's happening before your main program starts to execute. It's a really simple mechanism. Here's some code that's bound to get us in trouble. So main program's calling sub, sub is calling sub2 returns. So it doesn't do anything, but we can run it. And I'm about to call a subroutine. If I say next, I'll just come back from that call and I'm done. So when I'm about to execute this, I'm going to say step. I'll go in here and call sub2, I'll say step, and this will return. And then I'm done. See if I can hold on 1 second. Okay, so here's my main program. I'm doing calls, so that call queue is calling sub. Down at the bottom, I'm calling sub2, and so on. Yeah, I'll do this another time. But let me show you what we can do. Right? Suppose sub calls itself. Well, it's going to call itself, and the first thing sub's going to do is it's going to call itself, and the first thing that's going to do is call itself, and so on. Each time it makes that call, it has to save a return address on the stack pointer, right? There's a limit to how much space we have on the stack pointer. Eventually, we're going to run out of memory, and we get a seg fault. So that's a stack overflow. All right. I can do something cool in here. So let's make a local variable I, set it equal to 42 inside our function sub. And let's go ahead and run this. So I'm inside my function sub. I have a local variable I. If I step, I is equal to 42. Let's look at the address of I. It's 7 bunch of F's, E54C. Okay, I'm about to call my function sub, which is what I'm in right now. I'll say step. If I look at I right now, it's equal to 0. It's not equal to 42 anymore. This is a local variable, right? This is a local version of I. If I step, I can print I, now it's equal to 42, but if I look at the address of I, it's 7 bunch of Fs, E5, 1C. Different location in memory. If I step, and I print the address of I, it's now 7 bunch of Fs, E4, EC. So each time I call my function, I have local variables. Those local variables need to be stored somewhere separate from where they were stored before. Right? Where do they get stored? They get stored in the stack. So the stack isn't just for return addresses, it's also where your local variables reside. And so you can see where our stack is, right? It's 7 bunch of Fs, E4, EC. And if you actually look at that location in memory, you'll see our current value of I, you'll see the previous value of I. All this other stuff is information that was pushed on the stack when we made our call. Information like the return address. All right, so somewhere in here amongst all of these is the program counter of where that call to sub was made. So the stack gets used for a lot of things. It's other than the heap, it's the main place that we get memory from for storing variables and other information. All right, so we haven't talked about how to make a stack yet. There's one that comes with our PC. Right, most CPUs have a stack mechanism built in. The PIC processor has a stack. How big is the stack on the PIC? Remember? Ballpark? 10, 100 million? 64. Yeah, something around that. It's like 31-ish. It's 31 or 32 or maybe 30, depending on how you count. It's pretty small, right? On a x86 architecture, right, the stack is basically bound by how much memory you have. You have a bunch of memory, physical memory, which gets mapped to virtual memory, and some of that's used for your program, and some of it's for the operating system, and some of it is just used for the stack. And the stack basically starts near the end of memory and moves into the earlier parts of memory. And it can grow until it hits something that says, hey, this memory is in use, or it doesn't exist. So here the stack's pretty generous. PIC processor is really small. Some systems you can specify where the stack should be. Some systems like the PIC, it's hardwired as part of the actual silicon. Here's some transistors that make up the stack. All right, so as an abstract data type, if we forget about spring-loaded cylinders with platters that push plates up, or pieces of paper that we write things down on and cross them off, if we forget about how we implement a stack and we just think about using a stack, right, then we're thinking of a stack as an abstract data type. We're looking at how do we interface, how do we interact with a stack, and there's really just a few things that we want to do. We usually want some kind of initialization. So create an empty stack, for example. We want to be able to push data. We want to be able to pop from the stack and return whatever was at the top of the stack. We might want a function we can call isEmpty, which says is the stack empty. And we might want an isFull, which says is the stack full. Are we going to get an error if we try to push something? And maybe these are Booleans. And maybe push could be a Boolean, which tells us, you know, did I succeed in pushing or not? And that's more than enough for most most stacks, we could have, you know, reset, which throws away everything that's in your stack and just sort of sets it back to an empty stack. But mostly initialize, push pop, maybe see if it's empty. So not a whole lot of interaction points. So if that's how we want the user to interface with our stack, we can start looking at how do we implement a stack in, say, C. And there's two approaches we can think about. The first one we can implement using an array. All right, so how do we do this? Initialize an array. Let's suppose we're doing a stack of integers. Okay, so I'll have an integer stack bracket 10. So I can hold 10 things on my stack. I'm fixing the size of this structure. All right, if we think of the plate of dishes, and we think of this as the top of the stack, when you want to push something, you just copy it to stack bracket 0. Okay, in that model, if we wanted to push something else, we would take this element 0, we'd copy it down to element 1, we'd put our new data in element 0. And then if you want to push something else on, you'd copy 1 to 2, 0 to 1, and you put your new data in element 0. Okay, that's not very efficient, especially if your stack has a lot of stuff in it. You have to do a lot of shifting every time that you want to add. So instead of always adding at element 0, we change where we add, and so we have a stack pointer. And there's at least 4 different ways we can use a stack pointer. But we're going to say this is index for the next push. So I'm going to think of SP as the location where the next push data should be stored. So my initialization routine just has to say, set the stack pointer to 0. My push, if I want to push some number n onto the stack, to push it on the stack, all I have to do is store it at the location given by stack pointer. So this is just stack bracket SP equals n. Let's take the number you want to push, store it in your stack array. My first time I push, I'm going to store at location 0. What do I need to do to SP? Increment it so that the next time I push, I'm going to store at location 1. So I can store at stack SP++. Alright, so post increment, use SP, and then after you're done, increment it. So my first push goes here, and then my stack pointer changes to 1 and says the next push is going to go here. Next push will go in 2, and so on. Alright, how about popping?
SP minus minus, and then you want to return what was at SP. So you just return SP minus.
Alright, so let's say I do one push and I push a 42 on my stack. And my stack pointer is equal to 1. So if I'm going to pop, I want to return the 42 and I want to set stack pointer to 0. Right? So this is a pre-decrement. Right? Subtract 1 from the stack pointer, because stack pointer is where I'm going to push the next thing. If I subtract 1, it's where I push the last thing. and then return that value from the stack array. So now stack pointer is 0. And that gets returned, and the stack pointer has been adjusted. Yeah.
So when you pop something, are you also clearing the stack of that?
No, so that 42 is still sitting there,
Okay.
right? Which is kind of interesting. Because we're using the stack for local variables. What if your local variable had a password on it? And now you exit your function and all of that stuff gets popped off the stack, but your password is still sitting there in memory. And your program exits and another program comes in and gets random locations of memory and happens to get that location where your password is stored. Right? That's a security issue.
Is there like a technique to prevent that? It's just like flow, not flow, like just putting a bunch of stuff into the stack, like calling some function?
Yeah, so you could modify your pop routine to put a 0 into stack bracket SP and then return minus minus SP. Well, you have to do it a little differently, but do stack minus minus SP, save that somewhere to return, and then
Isn't it safer
clear
just
it
to
out.
hash passwords instead of storing online?
Yeah, so you really don't want to be dealing with plain text passwords in code anyway, but people still do. And when you're typing in your password, right, before that can get hashed, it has to get saved somewhere. And this is all like tricky stuff, right? I mean, usually you're working on your laptop, it's there, it's fine, but you know, on a system out in the wild, it's really tricky to sort of like clean up all those footprints. And even if you take the contents of memory and change it to something else, there's still residue of the old value there. And if you really want to be paranoid, right, this thing is a big radio. It's giving off electromagnetic radiation. Every time a transistor changes state, every time current flows down a wire, you've done physics, right? I don't know if you've done Maxwell's equations yet. Every time that you change current flow, you generate an electromagnetic field. And that radiates through the whole universe. So you sit in the parking lot with a receiver, you can pick up the EM emissions coming off my laptop. There's a possibility that you can tell what I'm typing, what I'm looking at, what calculations are taking place. And there's exploits that have been done with that. That's a whole program in the 80s in the government called Tempest. The government got really excited about trying to shield all of their sensitive equipment from electromagnetic emissions so that you could work on a computer without somebody observing the signals coming off of it. So there were like Tempest secured rooms that you could put your computers in and you'd work in there, and you got terrible radio reception. But yeah, there's all kinds of levels of paranoia. There's also Powerline Exploits. I read one of these a few years ago. You can plug into the power line and look at the fluctuations in the 120 volts coming out. And based on that, somebody was able to deduce where the code in a router was in authenticating a user. And by trying different passwords, it would determine at different points that the password was invalid, and they could tell how close they were to the right password by monitoring the power line down the hall from where the router was plugged in. And they were able to basically bootsy their way into the correct password. There's all kinds of stuff. All right, so stack implementation, right? Here's one way to do this. Push, pop. Let me show you a different way to do this. We can think of SP as the location for the next pop. SP tells us where we should pop the next thing from, right? The way we just did this, SP was one more than the last pop. So to do a pop, we had to decrement SP. If we think of it as where the next pop will come from, then our init function should say something like SP equals -1. Our push should be a pre-increment. right? So increment the stack pointer to the next location and then write into that location. And now SP is where that last thing was pushed. That's what's going to be popped next. And our pop well, SP tells us where we should pop from, but after we read that value, we'll go ahead and decrement the stack pointer. So we can do a push with a pre-increment or a post-increment. We can do a pop with a post-decrement or a pre-decrement accordingly. And those two techniques, different interpretations of stack pointer, but they basically assume you're going to start writing your stack from location 0 and move down to higher locations. Well, we can do an exact similar two pairs of implementations where we assume we start writing a stack down here at location 9 and we move up. And then this would become a post-increment, pre-decrement, and the other one would become a pre-increment, post-decrement. And so we got like 4 different ways we can do this. And some of them are preferred in certain situations. This is usually the one that I come to, but this is actually what the pick processor does, I believe. So some systems like ARM processors, you can choose how you want your stack implemented. There's a pair of bits you can set up. You can choose any of these 4 approaches, depending on what you're trying to do. Now, if you're writing a stack in software, right, you're writing C code to do this, you can do it however you want. If you're trying to use the hardware stack, you're usually stuck with whatever the hardware does. So on a PIC processor, it's a very particular order of operations. So how do you tell when your stack is full? Let's just stick with this first one, which is post-decrement for push, post-increment for push, pre-decrement for pop. How would we know if our stack was full? So if SP equals 11, it's definitely full. What about if SP equals 10? That's also full because SP is where we're going to push, and we don't have an index 10, right? The biggest index is 9, so it's actually full if SP is equal to 10, which is number of spots in the stack. Now we made a small stack, 10 elements, but we could have had init actually create a stack on the fly. We could have it do a malloc and allocate memory for, 1,000,000 spots. And then our stack would be full if our stack pointer equaled 1,000,000. And when is the stack empty?
If SP is negative 1. Or wait, is it post? Are you talking about post increment?
Yeah, this one.
Okay. So yeah, if SP is 0, then it's fine. So that's just negative 1, right?
Well, actually, if SP is 0, we've just initialized. SP is where we're going to do the next push. So if SP is 0, we're going to push into this first location, but we haven't pushed anything there yet.
Yeah, so if SP is negative 1, then it's... Oh, sorry. You meant empty down as well.
Yeah, yeah. So if SP is 0, the stack is empty. All right, so if you try to do a push, first thing you do is see if the stack is full. If the stack pointer is equal to 10, you can't accept that push. It would generate an overflow. When it's equal to 10, that means we filled in this last spot. That's fine. If we pop, we're okay. But if we fill in this last spot, SP is 10, and we try to push, we got to say stack is full. Generate a stack overflow. And if we're trying to pop, check to see if SP is equal to 0. If it is, say we got a stack underflow. Right? If we don't do that, we're going to decrement SP to -1, try to reach stack bracket -1. That might be a seg fault. It's certainly outside our stack. So what happens when you get a stack overflow? Well, I did that with my program, right? I had sub call itself a bunch of times, and it just gave me a seg fault. But how long does that take? Let's make an evil global. So every time I come into my sub function, I'm going to increment evil global, and I'm going to print out that number. And we'll keep track of how many times we call sub. So 174,000 calls to itself blew up our stack. That was a lot quicker than I expected. Let's just try something. Let's make some more local variables. Oops. Actually, it took longer to blow up. 174,588. 174,510. So the amount of space that's available on our stack is not always fixed. Sort of depends what else is going on. All right, what else do I want to say about this? See if it's empty, see if it's full. What happens when you get a stack overflow or underflow on the pick? We rarely talk about this. What? It catches fire, exactly. What?
The flag gets set.
A flag gets set and it does a reset. It jumps back to location 0 in your program memory and it starts executing from the beginning. But it sets a flag in that stack pointer register that says underflow or overflow. So theoretically, every time your program starts, you're supposed to check that flag, and if it's set, you know something went wonky. And you are running because you got an overflow or an underflow. So then you like set yourself on fire. All right, so we can implement stacks with arrays, and that's really what happens at the hardware level in most systems, because your stack is stored in memory. Your memory is really just a big array, right? So there's a register called a stack pointer, and we save your data at stack bracket SP, but really what's happening is you have, you know, SP is a pointer to an integer, and you just say star SP plus plus equals n. Store n at the location pointed to by SP, and then increment your stack pointer, or decrement it, or do whatever you're going to do. Right, and now SP doesn't have to point to location 0 of an array, it can just point to some location in memory that you mallocked. Okay, but we got another way we can implement. We can implement it as a list. And this is a whole lot more fun. So let's push a 10, make a new node 10, have the sentinel point to it. And this is null. Push a 20, make a new node 20, have the sentinel point to that. Right, 20 points to the 10. So insert at the beginning of the list. Push a 30. Well, we're going to make a new node 30. The sentinel will point to 30. 30 will point to 20. 20 will point to 10. So it looks like that. When you pop, just remove the first node. So when we pop, that's going to give us a 30. We're going to remove it from the list. The 20 is now at the top of the stack. If we pop again, that's going to give us the 20. That gets removed. The 10 is at the top of the stack. If we were to pop again, we would pop off the 10, but at this point we say push 200, that's going to create a new node 200, put it in the beginning of the list. And then when we pop, we'll pull off the 200, and when we pop, we'll pull off the 10. And now if we try to pop, that's an underflow. So this is a bit of an easier implementation if you've got a list package handy. It's fast, right? It's as fast as storing in an array because we don't have to move through the list. We just store right in the beginning. An underflow is easy to detect because with an underflow, your list is empty and you're trying to pop. And how do you know the list is empty? The sentinel is pointing to null. When does this overflow?
You run out of memory.
When you run out of memory, right? So malloc returns 0 while you're trying to make your new node. That's the only time you're going to overflow. Now you can put in something artificial. You can keep track of how many things are on the stack and say, I'm only going to let 50 things on the stack. But if you just write this, you know, like this, and you keep pushing things, your list just grows bigger and bigger and bigger. Eventually you can't malloc anymore and you're out of memory. And that's usually how stacks work, even when they're array-based, right? They're usually not artificially limited up front. They usually will consume whatever memory is available in that section of memory. So stack-based, list-based stacks are pretty easy to code up and pretty efficient to use. And we can peek, we can look at the top of the stack by just looking at the data and the node that Sentinel points to. That's easy. And we don't have a stack pointer here, right? So this is the pile of plates. The stack pointer is always right here, right? It's whatever the Sentinel is pointing to. All right, got the idea of stacks? Okay, so the dual to this is what's called a queue. And a stack is a last in, first out. A queue is a first in, first out. A queue, you throw a bunch of things into the queue, throw in an A, a B, a C, a D, an E. When you start removing from the queue, you don't remove the last thing you put in, you remove the first thing you put in, that's the A. Then you remove the B, the C, the D, the E. Okay? Classic way to think of a queue. You're in line somewhere. You enter the line at this point, you exit the line at that point. The first person in the line comes up here, they're going to be the first person out of the line. The second person in line stands here, they're going to be the second person out of the line. So if this is a checkout person at Freddy's, right, the first person in line is going to be the first one to get their groceries rung up. 5 other people come in line, 1, 2, 3, 4, 5, they're going to be served in that same order. The last person to go in here, they're the last person that's going to be served on the output side. So it's also a last in, last out. But fundamentally different behavior from a stack. Stack, the last person in would be the first person out. That's what happens when someone comes along and says, I can help you over here, and then the last person in line suddenly goes over and they're in the front of the other line. But a FIFO, right, that's the fair way to do it. Everybody's served in the same order. All right, so tomorrow's your midterm. Monday we'll probably spend talking about the midterm, so we'll get back to queues on Tuesday. We'll look at implementations with arrays and with lists. Lists are easy, arrays are trickier. And then we're going to start moving towards talking about trees. And that'll be sort of like the core structure we're going to deal with the rest of this course and a lot of 223. And that'll be a variation on lists, basically. All right, so I will see you tomorrow. Do not miss your midterm. That's my handy advice.